So if you get that and you get vapor pressure, the other ones are pretty easy to follow. Heat vaporization is very similar to that of boiling point because we're going to be considering all at constant pressure is essentially the amount of energy or enthalpy required to vaporize it. And so we can see this here. All of these have these types of intermolecular forces, and we can see the required energy. So it follows that if I have a high boiling point, I'm going to have a high heat of vaporization, just because of the fact that they're very related to one another. Surface tension. Surface tension is basically the skin that's across the surface of a liquid. And what's happening is that you have these molecules in the surface that are feeling this pull toward the bulk. So they're all feeling this pull toward the bulk. And especially with water. And when it does that, that's what actually helps us create our meniscus. If you think about the meniscus, it's kind of bent like this. Well, with aqueous solutions, because in the middle here, it's getting pulled down toward the bulk of the water molecules. And so these surface sites end up having much more attraction forces because they're starting to feel this pull toward the center of the bulk of those molecules. And so when that happens, and you get that, arrow is not very good, you get this pull down, what's going on is you create this skin. And this pull down has to do with how strong the intermolecular forces are inside that bulk. So if I have really strong intermolecular forces, that means I have a high boiling point. I would therefore have a high surface tension.
A paperclip is placed carefully in water, or rather on it. The metal clip floats because it isn't heavy enough to break the water's surface tension. By adding a small amount of soap, we reduce the water's surface tension. The paperclip sinks.
And so this creates a different type of intermolecular force because the soap leads to this dipole-induced dipole, which is actually going to reduce the amount of pull that you have in here, and therefore reducing the surface tension, it causes it to actually drop. As I had said, this is also related to what we call capillary action, or also why the meniscus forms in water. And this is because of these cohesive forces in the bulk pulling down on the surface. The sides are trapped by what we call adhesive forces to the actual glass or whatever the material is made out of. And so that's why you end up getting this concave meniscus. When you have substances, for example, like mercury, which don't have very strong cohesive forces, you actually end up getting a convex meniscus because of the fact that the cohesive forces are much weaker than the adhesive forces.
When a piece of paper is dipped in water, the water moves up the paper by capillary action. The attraction of the water to the surface of the solid paper allows the water to rise against the force of.
And so this is an important concept, especially when you're talking about rising against the force of gravity. One of the thoughts that you should be able to think about at this point is, especially with trees. So how do trees pull up the water, especially these huge redwoods? How are they able to pull up the water against all of that gravity when they're hundreds of feet tall? And so this is all due to capillary action. So the kind of the ending point here, in general, what you got to remember is once you get your boiling point, you're able to predict whether it's relatively high or relatively low. You then also know, well, if I have a relatively high boiling point, I'm also going to have a relatively high freezing point. So we didn't go over freezing point, but there's one thing to remember. We're going to get to that in the next chapter. If our boiling point goes up, we tend to have a relatively low vapor pressure. It goes down. Surface tension goes up, and so does viscosity. So these are good things, a good kind of guide to remember here.